Okay, so the next speaker is Dingyu Yang, and he will talk about transversality for coproduct and cobracket.
Okay, thank you for the introduction, and thank you for coming. Right, over the past symplectic talks, we know that holomorphic curves are very important in symplectic topology, and they provide rich source of algebraic structures. And given those standard input data, we have a symplectic form W and embedded Lagrangian L, and we can also allow some non-compactness provided they are like cross-section of contact manifold, which is all-dimensional analog of symplectic manifold. And for the Lagrangian, it's like cross-section is a Lagrangian, which the contact form vanishes on it. And you pick an auxiliary structure, almost complex structure, then you get a moduli space of G holomorphic curves. And in WL, it can have boundaries, punctures, and levels. There will be a picture in the next slide. And they come with the evaluation maps at punctures and also on the boundary loops. Okay. In talks of Kaya and also the paper of Chitebak-Leshev and Monkey, they have a conjectural picture where which says the codimensional one boundary of a moduli space under a given Hoffer energy can be written as a sum of things of a combinatorially simpler moduli space through evaluation maps of some operations. For example, the loop bracket and cobracket are the operation on the loop space. And here is the picture. For example, we have a genus 1 surface with the two boundary components. And over here, we have one positive puncture and one negative puncture. And here we have a two positive puncture and one negative puncture. And it maps into, for example, here we look at a symplectization, which is just R cross with a contact manifold. And we draw the picture of this curve inside this, and over the puncture, near the punctures, it asymptotically converges to the periodic, to the ripcord or rib orbits. And on the boundary, it lies in this Lagrangian R cross with S. And the boundary of this can be decomposed into several terms. It can break into two levels, and you have fiber product over two such things. And there are also degeneration of domain complex structures, which gives loop bracket.
So fiber product is where it splits along periodic orbits.
Yeah, or the chord. Here. If you have a loop connecting the same boundary component, then you get loop bracket. If connecting different boundary component, you get a loop cobracket. And you could have like one domain or two domains, depends on whether it's separating or not. And here there are two transversality at place. One is this intersection type of operations on the evaluation maps. Then not transversing like as it is. And also there's very non-trivial transversality problem for this domain moduli space. They are like solution of the bar equation, which is a Fredholm problem with the domain variation and analytic limiting behavior. So it's very bad in general. For transversality of this basically gives you a induction scheme to achieve transversality. For that to work, you need to define the intersection type of operations geometrically and also at chain level, because you already have a generalized space with corners intersecting together. And we require smoothness of the domain space and the maps. Okay, so let's look at two operations in string topology which give rise to this loop bracket and cobracket. If you look at two family of curves, I draw in black and red, and the trace of this line denotes the base point. And over the point where they intersect, you can concatenate the loop together. This is the loop product. But when you have a single family of loops, a my self-intersect like this, and maybe further, and then you cross the domain with the time interval and look at this self-intersection space-time where the, for example, here, and look at the time where it self-intersects, and there are 4 places for this thing. And in this picture, you notice 2 things. One is, if you look at the domain here to be the domain of the coproduct, then it's very bad, because this line and this line, the whole domain over 0 and 1 time, will always lies in the trivial self-intersects. So that's very bad transversality. And also, although loop here and here are the same, but the coproduct defined here and here are different. So we need to cut it open like this. Right. So we now focus on the coproduct because it has the most severe transversality issue. And also, loop product is worked out by Ari. It's this joint work with Manuel Rivera. Chad Sullivan in 2002 introduced this coproduct on sufficiently transverse chains. Then Gretzky Hingston in 2007, they defined dually. They defined on the cohomology modular constant loop product structure, which is this homology level. And so to look at this again, so we have a family of loops where there's a self-intersection, then you can split like this. And this is just, if you define evaluation map like this, at 0 and t. 0 is the base point. And for the later purpose, I denote interior evaluation for the t lies in 0 and 1, away from the base point. The self-intersecting spacetime is just the preimage of the diagonal. As we saw, it's never good unless in the very special cases. So how can we make this into a manifold to be the domain of the coproducts? Okay, the idea is this. You can try to thicken this chain phi into some bigger chain with more direction in the domain, so that this interior evaluation is transverse to the diagonal. So this thing here is a manifold. Then you hope taking the closure as this t goes to 0 and 1, this b still remains a manifold. And then you kill the extra direction you added by drawing formally a Tom form, mu. Okay. And to achieve this, we make some choices, and alpha is just a device that stops the loop near the base point. And lambda 1, lambda 2 is just 2 cutoff functions. Important thing is that they both vanishes at the base point, and also for non-base point time, there is always one of them which is non-zero, and lambda 2 vanish near the base point, and the lambda 1 has specific behavior near the base point. And then you choose a Riemannian metric on the M, which has an injective radius delta and give you an exponential map where you can add vector fields. And the thickening is defined this way. It looks complicated. It's basically just along this stopped loop, you use 2 vectors to move this around, scaled by this lambda 1, lambda 2. And because you only want to thicken the finite dimension, you thicken at 0 and half, and then you parallel transport them around. So you form like 2D dimension thickening. D is the dimension of the M. By construction, because at the time 0, it does nothing. It's original loop at the time 0. But at the other non-zero time, there was one of them being non-zero, one of the cutoff function, and you have a like tangent space worth of movement to make it transverse to a diagonal. So this ensures the preimage of the interior evaluation to be a manifold. Okay, for t close to 0, you can look at the self-intersection equation. Maybe I'll write here. I think if I draw high enough, people can see. So if you have this thing at 0 and at t, and this just the original thing at 0, and this is just this loop x and composed with alpha. The double direction won't appear, and for t small enough, we have this thing, and you can solve this, and you can express v in terms of a smooth function which smoothly extends across 0. And so if that function lies inside this delta open ball, then it can be uniquely solved. And I chose it to be identically 0, so this function will be 0 near there. So this will be true. But the way I set it up this way is that actually this can be done without stopping the loop as well, by smoothly assigning every loop a pair of things in this construction. Okay. So you choose a term form which only depends on m, basically integrating along the fiber to be 1, and it's compactly supported inside this open delta ball. And so because the output will give you a form, so better consider input to be a pair where you have a geometric chain with the corners and a compactly formed eta. And then you have this closure of preimage of interior evaluation of the diagonal P, I denote it as a P phi. Over there, you can split the loop open. And because the loop might not be smooth over the cut point, which is the new base point, you can also smooth it via this same alpha. And to get a form here, you first pull back the form into a thickened fiber, wedges this term form, which kills the thickening direction, and pull back to the space-time and restrict to the P phi. So this is the output. This gives you a, it's not a chain map yet, but Kingston and Wall, they have algebraic modification, which gives the chain map on the absolute chains, which is alternating sum of things defined on the same P phi. And in progress is with the Manuel, I try to establish the co-associativity of V on this thing up to higher homotopy, so it gives a co-infinity structure. We have this is because there's no canonical way to turn this into a tensor product of things. And this script C is a de Rham chain, which I'll briefly review in the next slide. This is expected to agree with the homological level description of Abadandolo-Schwartz and also chain level description of Ekholm-Wansha's coproduct on the symplectic homology of cotangent bundle. Maybe I still have a little time. So this construction basically, you can treat U as a family. If you look at here, and this denotes the base point, and you consider here, before we just consider here with the base point at 0, but if you allow the base point to move, and suppose this is over the original thing, and you have self-intersection at the t, then automatically it tells you that when base point is t, there is self-intersection at 1 minus t. And then you can just thicken along radial directions and do the basically do the evaluation of two time variable 1s base point 1t, and this you get a homotopy of commutativity, and you symmetrize it, you can get a loop cobracket. So let's briefly review the complex setup there. It's introduced by Fukaya, and Airy used it to establish loop product and bracket, but without boundary and corners for Airy. Well, generally, over modulo technicality, it's just a hybrid between geometric chain and the Rham cochain. You expect the familiar property, but the thing here is because this dimension can change simultaneously as long as difference remain the same as the degree. So there should be a way to relate different dimensions together. If you thicken the chain, but along the thickening fiber you do nothing to the map, then for form along the thickened domain, you can integration along the fiber get this two should be the same. And the boundary operator is the combination of the two. The upshot is that it's quasi-iso to singular chains, and it's good for higher homotopy because if you perturb the phi, usually there's a step you want to take a generic point, and to cook up homotopy between two such things, you need to look at the different space for cobordism and so on. But here you just keep thickening and keep track of it using Tom form. The domain spaces are actually not honest spaces. They are generalized spaces, can be smoothly described by Hofer-Wysocki-Zenders polyfold theory or Fukaya or Ota Ono's Kuranishi structure. My thesis is about the correspondence between these two virtual structures. What I did is I lifted Kuranishi theory to an equivalence class level and show those both frameworks are equivalent. And from either of the structure, the evaluation map, we can get a Rham chain of the loop space. Okay, so this fits well with the virtual theory before. So from the same construction, we can get cobracket on S1 equivariant chains. And the near future goal is that consider the rotation operator and the compatibility with that, and the non-marked point version of Airy's loop brackets on the equivariant chains. We hope to establish a compatible bi-Lie algebra structure up to higher homotopy. It's called IBL infinity by Chilichbach, Fukaya, and Lashev. They worked out algebraic theory for cyclic A-infinity algebra of finite dimensions. But to generalize to this setting, there are very still in progress. This provides another way to do this. The eventual goal is use this IBL infinity structure to achieve transversality inductively. And the moduli space in the codimensional 1 degeneration picture will satisfy this Morikatan equation. I can twist this IBL infinity structure filtered by energy. And hopefully this will yield invariance for a pair, Cantor manifold and the Lagrangian, independent of auxiliary choices and the contact form. This contains relative SFT. Even with the genus and the multiple boundary component, it will be like relevant. For example, consider you splitting a Fukaya algebra along a contact hypersurface, for example, which is a superficial example. Okay, thank you.
Thank you very much.